I think the SMR ones are really, really interesting because there's this chicken and egg problem with the NRC, which regulates nuclear, where you need to show them data that your reactor is safe in order for them to license you to build the reactor. But you can't get the data until you get the license. And so there's this like big chicken and egg problem going back and forth. Companies like Radiant are trying to overcome that by working directly with the Department of Energy and something called the Dome up in Idaho at Idaho National Labs. Some people are going through the DoD where you can test with the DoD and get that data. Some people are going abroad to get that data, but it's this like real big bottleneck and chicken and egg that you aren't allowed to get the data that the NRC demands.
The Dome is a existing 80-foot diameter structure. That's actually this giant cylinder, half of which is underground. It was built in the 1950s at Idaho National Lab and had the experimental breeder reactor 2. And so we're building a reactor here right under the quality program that's been approved by the lab. So we'll do like an acceptance test and then we'll ship it out this door right behind me, but then it'll culminate in this 150-hour endurance run. What we're trying to do is around the clock with 3 shifts of operators, keep the thing running for 150 hours continuously without having to do anything. And that will be a really great proof of reliability of the system. And then we'll go to focus on getting units out to customers and the factory beyond that.
Probably our most fundamental conviction at Valor Atomics is that you actually need to build nuclear reactors in order to build nuclear reactors. And this sounds a little bit circular, but it's actually quite serious. All technologies evolve through actually building things. It's the only way that technology evolves. And unfortunately, in the United States, it's essentially impossible to do that. Our regulatory environment is not formatted in a way that allows entrepreneurs like myself to quickly build a small reactor, test it out in the desert, and see if it works. And this is the only way that advanced technology moves forward. So as a team, we got together and we said, where's the best place to build a nuclear reactor today? And we chose the Philippines. The Philippines has been an incredible partner for us. They're eager to build. They want to see nuclear happen in their country. They really need it. They're an archipelago nation, 7,000 small islands spread throughout the South Pacific. And they need nuclear in order to thrive as a civilization. And so they're willing to work quickly with us to go through the R&D necessary to bring nuclear back.
I think there's going to be a winner-take-all approach, but I don't think just because of the CapEx-intensive nature and the supply chain-intensive nature that it would be possible for a single entity, a single company to be a winner-take-all in the sector. I think you're going to see one company, I hope it's ours, break through with a model that shows the successful economics, that shows repeatability, that shows scalability. And then you'll see a lot of fast followers into that segment. And over time, then it'll be a different type of competition. It'll be a competition over market share instead of race to who's first. Potentially, for the first time in human history, if we're able to really take nuclear energy and realize its full potential to fully decouple environmental impact from the energy source itself, and therefore create a world of abundance without consequence.
Fusion is the process that powers the sun and all of the stars in the universe. So you could almost say that like the universe's choice of preferred method of making energy.
It's the simplest form of how the universe works. So taking the simplest atom that's most abundant and creating the conditions for it to fuse, which means for 2 hydrogen atoms to combine together. And the famous Einstein E equals mc squared equation, if the small mass of mass is lost, multiplied by c squared, which is the speed of light squared, which is a very large number, you can release a significant amount of energy. I think without fusion, the whole universe would be just a blob of hydrogen. So all the atoms that exist are due to the fusion reaction that's constantly going in the sun and in our stars and in the solar system.
It's really a process that generates massive amounts of energy per unit fuel. So that means that it really is abundant energy that you would be able to get out of this.
The prospect of fusion is actually much better now than it was even 10 years ago. It suddenly turned into a factor in the fuel mix of future power in a way that I would not have said even just 10 years ago.
Fusion, which is like this golden child in the future that hasn't had to deal with any of the challenges that fission had. Fusion, I love. I think the fusion industry tries to throw fission under the bus a little too much by being like, no, we're not that thing. That's dangerous and messy. Like, we're great. But fusion is amazing, and I hope we get fusion power soon as well.
We are just in a glorious set of flowering Cambrian explosion of types of fusion power ideas. A decade ago, there were 10 serious fusion companies, and now there are over 45. I mean, it's really going.
Fusion power is cool. Fusion power is the sun, and all my other favorite stars. It's not really in doubt that it's physically possible. We just don't know how to do it. We're not smart enough. We haven't figured it out. We haven't put enough money into it yet.
I get a feeling that there really is something going on there, some physics that we don't understand. But the bottom line is very seriously that we don't understand.
A couple years ago, there was some really big news out of California. There's an experiment there called the National Ignition Facility, or the NIF. They actually fire a bunch of lasers into a capsule, essentially, and heat that capsule to intense pressures and temperatures. And then that capsule has a fusion event. So that's called inertially confined fusion.
NIF is a giant laser. It's over 400 megajoule of laser that deposits around a couple megajoules on a target. And then what happens essentially is just if you look at the energy deposited on a fusion target and think about it as the size of your pinky nail, a sphere that has fusion fuel, and that sphere, the energy deposited to implode that sphere was actually less than the energy the target produced. So after NIF demonstrated that fusion is possible, so now it's about a race of how do you make this commercial, which means making the unit economics work. How do you get it to be repeatable? So that means, you can fire at a point where you can have a baseload fusion power source, which is a really, really hard problem because we need to fire, one shot a minute or eventually one shot a second. So there's a significant, engineering challenges to get to a high repetition rate such that we can use fusion as a baseload power source. And then after that, you have to think about what we call Q commercial, which is, the commercial feasibility of the project.
If you want to make this a technology that gets out to the whole world, you have to make it economically competitive. Even if you get this to work and it costs 100 times more than electricity, nobody's going to sign up for that. So it has to be something that, even when you start, has to be close to the cost of electricity, what it is now.
And so fusion fuel is abundant. It's in deep sea water. It's safe. There's just no long-lived radioactive waste. It's on demand, so it's not geography dependent. You don't have to wait for the sun to shine or the wind to blow.
That, combined with the fact that you're not burning that much of it to emit energy. So compared to chemical reaction, is about 1 million times less efficient than a fusion reaction. So per unit of fuel, not only is the fusion fuel the most abundant fuel in the entire galaxy, it also happens to be the most efficiently burning fuel by a factor of 1 million.
I think there's at least a couple more stages to go in the technology before you get to something you'd really want to try and run the world on, because of the fuel mix that they use in the best experiments now is a mixture of deuterium, which is fine, and tritium, which is not fine because it's radioactive and it costs $30,000 a gram. So you don't want that. You don't get no low fuel costs when you're using that.
Those numbers really matter when you want to make energy really abundant and really cheap, such that you don't have to worry about how much is your computer consuming or all those data centers need to operate, so we can power a futuristic civilization. And our mission is to accelerate the world's transition to fusion energy while safeguarding humankind. Fuse is working on a direct drive that already saves 10 times energy efficiency, which has been proven on the Z machine. Fuse, the Titan technology, is the highest efficiency driver ever built, going from 30 to 40%, which is what current pulse power architecture energy efficiency is, to over 89%, which is what we've experimentally demonstrated and peer-reviewed on our machine.
My name's Brandon Sorbaum. I'm the Chief Science Officer and one of the co-founders of Commonwealth Fusion Systems. A tokamak is essentially a lot of very, very strong magnets arrayed in a donut shape. So the science behind tokamaks is probably not super widespread as far as something that people learn in school, but it's actually been studied quite extensively over the past 50 years. So as far as the science is concerned, we actually have a pretty good handle on it. It's really the engineering of this machine, making really, really strong magnets that can take that plasma and squeeze that plasma. And a big piece of our company in the early days was really proving out a whole new type of magnet technology that makes very strong electromagnets out of a device called a high-temperature superconductor. What we're trying to do is we're trying to create essentially a miniature star here on Earth in a tokamak. And we're building in this room behind me, we're actually starting to build that tokamak. And on our site, we also have a manufacturing facility that is producing a lot of the components that are going to be put into this device. Those magnets produce a very strong field that compresses this star, this plasma. So stars are made of a material called plasma. It's the fourth state of matter. And plasma is electrically charged, so we can use magnets to confine this plasma and to keep it safe from its surroundings so the plasma can keep going and keep producing heat, which we can then take the heat out and convert it into electricity and send that electricity anywhere.
So right now, Titan that we built is a 1 terawatt driver. So 1 terawatt is roughly 20% of the whole world's power generation for a few nanoseconds, or equivalent to the whole Western Hemisphere power generation for a few nanoseconds. And so what we use Titan is not a fusion machine on its own, but it's essentially the pulse power driver that would deliver the electromagnetic force required to implode and create fusion reaction. So we'll need on the order of like hundreds of Titan at machine scale that's producing power, like commercial power generation. What we need to drive down is the cost per joule delivered on target. So if you think of the objective of Titan as how can we reduce the cost of a joule that we deliver to a target, and then from there on, you can increase the target design efficiency such that you can increase your neutron yield, right? So there's two functions that are really important to optimize when you think of a fusion power output. One is how much does it cost you to deliver power on a target, and that's dollar per joule. That's what Titan is really focused on. And then the second point is on how much, what's the gain efficiency of your target. And right now, Fuse has demonstrated we have the cheapest and most reliable source for high repetition rate to deliver energy to a target. And then the next step would be on working on target designs that would essentially be high gain. And here on targets, there's significant work already going on national security by Los Alamos, Sandia, and Livermore on doing better and better target designs.
The other milestones that we are reaching as a company, right now we're building this device called Spark, a commercial prototype of the device itself that will make a bunch of fusion heat. So Spark is going to make over 100 megawatts of actual heat from fusion. That's a lot of power's worth to make in a device. And Spark is going to be the first commercially relevant net energy fusion device. So an exciting development in the last couple months is we've actually selected the site and secured the site for the first ARC power plant. And so this is a grid-connected site that is in Virginia that we will be building the first fusion power plant on that will provide fusion power to people. And we plan on building a whole bunch more after that. But it's really exciting, and it really speaks to how close this technology is that we've already secured a site that's connected to the grid to build this technology on. So this isn't something that's far off in the future. Like, this is happening right now.
I'm cautiously optimistic that we're going to get Mr. Fusion or something like it by the end of the century.